Hello everybody, welcome to the rotational motion video. So in this video, I will introduce the rotational motion, which is a brand new motion to us, and how it's different from the translational motion we used to learn. So a translational motion means an object is either traveling at a constant velocity or accelerating towards a certain point with a certain distance and displacement. But however, rotational motion is different from that. Rotational motion doesn't move towards a point, it just stays there. And instead of finding the distance it has been traveled, we're looking for a point on this circle and we're actually looking at the angle it has been traveled. By mentioning the angle it has been traveled, I have to introduce a whole new concept of radian. So radian is a new measurement of the angle, and it's similar to degree, but it's measuring in pi. So to convert degree to radians, you just simply using the formula showing there. Radians equals to degree times pi divided by 180. So if you have 90 degrees and you want to convert into radian, you multiply 90 by pi and divide by 180, and you can get pi over 2, and that's your radian. Simple and easy. So in order to find the angular velocity in a rotational motion, which is represented by a Greek letter omega, so omega is actually equals to the radian it has traveled divided by the time. So very familiar, right? It's similar to the translational motion, which is dot d over time. And instead of d, we have theta here. That is just for one point on the circle and the velocity of this point. But we also have tangential velocity. So tangential velocity is the velocity on this point, which is perpendicular to the radian. And radian is the only thing that makes this whole thing different. So in a circle, if we have a point closer to the center point of the circle, and we also have a point that is far away from the center of the circle, if the circle rotates, and the point that is far away from the center travels like a further distance than the point in the middle, which is that point had traveled more arc than the inner point. So tangential velocity of a point is all depends on the length of the radian, not the radius. It all depends on the length of the radius. So if the radius changed, the tangential velocity changed. So in rotational motion, you can pick any point in this object you want and to calculate any of the velocity or acceleration. And it's also a periodic motion. If you draw a function, it's going to be like sine function like this. So per one period, the point you pick returns the original place. It doesn't move anywhere. So the frequency of rotational motion is one revolution over time, which means but we also have that omega x equals to theta over t, and one revolution equals to 2 pi r. Therefore, we can get that omega actually equals to 2 pi times the frequency. So you get another way of calculating the frequency. And now it comes to the angular acceleration, which represented by the Greek letter alpha. So alpha is equals to the derivative of the angular velocity divided by the time. So isn't that familiar? Isn't that like the v2 minus v1 divided by time? Just like we calculate, just like how we calculate acceleration in the translational motion problem. So the derivative of the angular velocity means the change between that two points. So it's pretty much like v2 minus v1. And it's using the same concept. And radical acceleration is equals to omega squared times radius. A represents like any point in this object, and acceleration of this point. But a tangential acceleration only means that single point, that specific point, like the acceleration of that point. And radical and tangential are two different things. Like radical acceleration can represent any point in that object, but tangential acceleration can only represent that single point. It's the exact value for that exact point, but not for anything else. After learning all these formulas and equations, now we have to do an example problem to test out our skills. So the question is, calculating the angular acceleration and deceleration of a bike wheel. Suppose a teenager puts her bicycle on its back and starts the rear wheel spinning from the rest to a final angular velocity of 250 rpm, which is revolution per minute in 5 seconds. So the question is, what's the angular acceleration in radius per second square? In order to do this question, we have to list all the givens and unknowns. So the question is asking for the angular acceleration. And we have omega, which is the angular velocity, and we have the total time. So alpha is equals to omega divided by time. So we just simply put our givens here. So 250 rpm over 5 seconds. But revolution per minute, this is not the unit we want. We have to convert it into radians per seconds. So now we have that omega equals to 250 revolutions per minute times 2 radian over 1 revolution, and it cancels out to the unit of revolution, and times 1 minute over 60 seconds. So after doing all these calculations, we got 26.2 radian per second. So again, alpha equals to omega over divided by time. And we just got our omega in the correct unit in the last step. So 26.2 radian per second divided by 5 seconds. The answer is 5.24 radians per second square. And it's essentially the final answer of this question because we have the correct unit and we also have the correct number. So in conclusion, rotational motion is not that different from the translational motion that we used to learn. They share a lot of similar ideas like the formulas of velocity and acceleration. The only thing changed is the distance or the displacement changing into angles, and we measure angles in radians, and that's the biggest problem we have in rotational motion. And there are also many interest theory of fact in rotational motion, which is different than the translational motion. And yes, and that concludes my introduction to rotational motion. Thank you for watching.